السلام الوطني لدولة الكويت. All rise up please for the national anthem of the state of Kuwait. السيد كايل ميسون المدير الإقليمي لشركة مارك فورد. Mr. Kyle Mason, Regional Director of Mark Ford. المهندس عبد الله الصفار المدير التنفيذي لمانيفاكتشرنج رابت تكنولوجي. انجينير عبد الله الصفار CEO مانيفاكتشر رابت تكنولوجي. معالي النائب هاني شمس Parliament Member His Excellency Mr. هاني شمس. معالي الوزير السابق المهندس محمد بشهري Former Minister Engineer محمد بشهري. ضيوفنا الكرام السلام عليكم ورحمة الله وبركاته. في البداية بالنيابة عن اللجنة المنظمة لمؤتمر تكنولوجيا المستقبل والتصنيع الإضافي الكويت 2022 أود أن أتقدم بوافر الشكر وجزيل الامتنان للسيد كايل ميسون المدير الإقليمي لشركة مارك فورد على حرصه وتفانيه وتواجده في هذه المناسبة، والشكر موصول أيضا للمؤسس المهندس عبد الله الصفار أيضا على تفانيه في تحقيق هذا الحدث. ولا ننسى زملاء المهندسين عبد الرحمن الرئيس والمهندس ناصر عبد العزيز، وأيضا الشكر لكل من ساهم في تحقيق وإنجاح هذا المؤتمر. حضورنا الكرام، استطاعت اللجنة المنظمة أن تجلب أفضل الخبرات العالمية والعلمية لعرض آخر ما توصلت إليه التقنيات الحديثة، على سبيل المثال لا الحصر، الطابعة ثلاثية الأبعاد والروبوت، والتي تعد الأفضل في العالم من شركة التصنيع الإضافي مارك فورد. نتمنى المزيد من التطور والتقدم لوطننا الغالي والتوفيق للجميع. Our esteemed guests, in the beginning, on behalf of the organizing committee of this conference on future technology and additive manufacturing Kuwait 2022, I would like to offer my sincere thanks and gratitude to Mr. Kyle Mason, Regional Director for Mark Ford, for his dedication. Moreover, great thanks to the founder, Engineer Abdullah Safar, for his sincerity, dedication, and concern. Great thanks the thanks are extended to his colleagues, Engineer Abdurrahman Al-Rayis, Engineer Nasser Abdul Aziz, and thanks to everyone contributed to the success of this conference. Our honorable attendance, the organizing committee was able to bring the best scientific expertise to display the latest modern technologies, for example, the 3D printer and the robot, in which is the best in the world from Mark IV to additive manufacturing. So we wish further development and progress to our beloved country, the state of Kuwait, and good luck to you all. والآن حضورنا الكرام، الكلمة للمؤسس المهندس عبد الله الصفار المدير التنفيذي لشركة Rapid Manufacturing، فليتفضل مشكورا. As for now, I would like to call upon the founder, Engineer Abdullah Safar, for his opening remarks.
السلام عليكم. ما بيطول عليكم، بس بقول شغله واحده. احنا نبي ان هالتكنولوجيا هذه الناس تعرف عنها وتبتدي تطبقها، سواء ان اما تسوي كابي حق السيستم اللي احنا مسوينه، او ان تتعامل ويانا. فيبنى السيد كايل علشان انه هو يشرح لكم التكنولوجيا اللي قاعد نستخدمها وشنو ميزاتها والاستخدامات اللي قاعد تستخدم في جميع انحاء العالم باستخدام الاديتيف مانيفاكتشرنج او التصنيع الاضافي. ويعطيكم العافيه. I think Kyle. Yeah, الأخ فريد، مهندس فريد.
Thank you. كل الشكر للمؤسس المهندس عبد الله الصفار على الكلمة الطيبة والمقتضبة والقصيرة مثل ما يقولون. Great thanks to the founder engineer Abdullah Safar for his nice word. And طبعا والآن حضورنا الكرام سيقوم المدير الإقليمي لشركة مارك فورست بإلقاء محاضرة وهي عن manufacturing reinvented. طبعا نبذة عن المحاضر مشاهدينا الكرام أو حضورنا الكرام. The presentation will be conducted by a graduate from Union College in New York, has more than 5 years of experience in mechanical engineering and 3D printing. His presentation has the title of Manufacturing Reinvented. Let's all give him a round of applause for Mr. Kyle Mason from the United States of America. تفضل.
All right. Thank you, everyone, for having me. Excited to be in Kuwait for the first time. So this is my first trip. So wish it could have been longer. I'm only here for about 24 hours, but we'll definitely be back in the next couple of months to hopefully do this again. And so as I go through this, the topic of this presentation is why build an additive manufacturing strategy. This is obviously very, very relevant in today's society in terms of building robust supply chains and trying to figure out ways to be more resilient when trying to manufacture parts. So manufacturing reinvented is a term that we typically refer to at Mark Forge commonly. A little colder. But either way, I'll dive right into it. If I'm talking too fast, just wave me down so I could slow down. But we have a couple of topics today. We'll talk about why additive manufacturing, why now, why is this something that should be important and something to review. We'll talk a little bit about Mark Forged. I try not to go into all the details there because we can talk about it after and look at the printers directly. We'll talk a little bit about customer testimonials because that's really what's important is how are people using it today, how are they capturing value, and how do they adopt this in their large organizations. And then business value. You know, if this obviously doesn't have a business purpose, then there's no reason to get into additive manufacturing. So you need to understand where this is applicable, what kind of value it drives for your company, and how can you scale that to drive even more value over time. So a little bit about myself. So again, my name is Kyle Mason. I'm currently living in Stockholm, Sweden. That is where I've been based for the last 7 months. But I've been with Mark Forge for about 5.5 years now. I started off in doing sales and have migrated from the US over to Europe to help run the sales team over in this area. I've been supporting the Middle East for the last 3.5 years, so I've had a couple of visits in this region and I've spoken and met with a lot of different clients doing different things, education, government, the private sector. And my background is mechanical engineering, so I primarily studied mechanical engineering in school where I was exposed to 3D printing and really what pushed me into exploring this as a professional career. So we'll talk about why build an additive manufacturing strategy. Obviously, adopting additive is an important aspect in today's society, and there's a lot of reasons why. We've all seen this photo before. Everyone is feeling the pain of increased lead times, difficulty sourcing parts, increased costs, and overall unpredictability of the supply chain. There are tons of macro factors that are impacting the way we manufacture parts that are generally out of our control. But how we manufacture is absolutely something that we can control and can influence to the point where situations like the Suez Canal don't impact day-to-day operations. Obviously we're seeing a lot of that pain today with inflation, the war in Ukraine, the after effects of COVID. These are all things that we can have very, very limited impact on when it comes to day-to-day operations. So the small things we can control and take under our influence, and that's really going to where we find the most value. So when we look at the traditional supply chain today, it's a complex web of steps that each incur their own costs, their own lead time. Each step represents a potential node of failure that can add unforeseen costs and delays. So the goal is to mitigate risk. And that's simply simplifying the conventional supply chain to basically 2 steps, design and print. So what does it mean? It basically means demand and planning doesn't really matter. Production becomes local consumption. Logistics are radically simplified to the last mile. New development cycles are dramatically shorter. Hardware innovation accelerates and costs are massively reduced. So Now, traditionally, this ideal of additive manufacturing supply chain can only be applied to prototyping due to the limitations of technology. However, we come a long way, and the technology has grown to cover a much wider range of applications, from machining tools to certified end-use parts, and many are adopting these methods. So each industry has their respective leaders that have already started their additive journey. Already these industries are facing challenges that we discussed haven't necessarily created this revolution, but it's been accelerating the momentum, and it's clear that we need to act now to stay agile, competitive, and on the cutting edge. So these are obviously a lot of the companies that have seen benefits and have been adopting it for 20 plus years at this point. Additive is nothing new. It's been around for quite some time, but there has been this traditional hype or curve where there was a lot of failures early on, and we've learned from those failures, and now additive is getting to a point where it can be adopted in scale. So I'll talk a little bit about the digital forge, and that's kind of our fancy term for our additive manufacturing solution, but it really combines two things: traditional manufacturing, what we expect and what we know, and bringing a digital aspect to it, and combining those two to have a much more agile and responsive manufacturing platform. So with Markforged, I'll talk a little bit about who we are, what we do, and why we do it. Our objective is essentially to build the largest network of connected 3D printers in the world that are addressing mission-critical applications at the point of need in a simple and easy-to-use platform. So if we look at these, we look at software, we look at mission-critical applications, we look at bringing the problem to the point of need, the manufacturing to the point of need, and we have a leadership team that's really driving that. So the mission is being driven by this team of highly qualified, motivated individuals that have a vast experience of knowledge and experience in both the additive sector and technology in general. And behind this leadership team is upwards of 500 employees across 5 continents and 3 core regions: the North American, EMEA market, and Asia Pacific. So we're a growing company, and just to kind of demonstrate where we've come over the last about 8 years that we've been a company. So the current state of that goal of driving the biggest network of connected 3D printers is about 15,000 printers scaled globally, over 60 countries, with 100 partners globally supporting that print farm or that fleet of printers, including our MT. So when we look at the network of connected printers and users, we see a lot of a collection of common goals. 1, people are trying to digitize their manufacturing. 2, build products more efficiently. And 3, become more agile and responsive when it comes to unforeseen global macro factors. We'll take a look at the slide again a little bit later on in the presentation, so keep in mind some of these terms as we look through some of the customer testimonials and the technology as a whole. So this is Markforged. To support our mission, there are pretty much 3 main pillars that need to be considered: hardware, materials, and software. We've essentially designed and developed a robust fleet of composite and metal 3D printers that are built tough enough for the factory floor. They're meant to withstand it. You can see them for yourself. They're all aluminum bodies, and they're built tough. They're not plastic machines. They're not made out of wood. These are real industrial tools. We manufacture all of our own materials that are designed specifically to operate in those printers to ensure reliability of the system and the best mechanical performance. So a tool that you can rely on for time and time again. And lastly, we have developed and continue to develop our own cloud-based software program, which is the backbone of the Markforged solution. Many users tend to focus on hardware and materials, aspects of the 3D printing journey that are really a part of the conversation most of the time. How fast is my printer? How big is it? What materials I can produce? But what we forget about is the software component and how critical of a component that is for creating scalable processes and a successful adoption across the entire organization. If you are a Saudi Aramco, it is extremely difficult to introduce a printer that has, or multiple printers in that case, that have lots of different softwares, lots of different materials that aren't built on the same platform. So when we're talking about scale and you're trying to build a new process in a large company, you need to have processes that are backed by software that allow you to adopt it, educate, and scale it on a global nature. And software is really the backbone of that type of journey. So we'll take a look at each of these pillars individually, and just a little bit of background with the technology that Markforged has is there's obviously, it's a very saturated industry. You can see lots of different types of 3D printing technologies. I know the font is a bit small there. But there's SLA, there's SLS powder bed systems, there are extrusion systems, there's light curing systems. 3D printing is a very, very saturated market these days, and it's hard to figure out what's right for you. Where Markforged situates is in this column right here. This is what we call fused filament fabrication. And essentially that's a fancy word for extruding material layer by layer until you have your 3D printed geometry. So I like to compare it to a glue gun, just extruding materials layer by layer. It's as simple as possible. This is probably the most common form of 3D printing in today's market, which the benefits of that are it's easy to use, it's easy to scale, people are very familiar with it. So once you start to build in higher performance materials, better accuracy, more speed, it becomes a very, very scalable process. So when we look at our hardware, all of our hardware is built with strong aluminum frames to ensure a rigid printing platform made for the manufacturing floor. The rigid frame really helps to maintain extremely high accuracy and repeatability between printers. So they're all overbuilt in that case, so the technology can grow and develop over time without changing the hardware. For example, so we do a lot of that through software. Software is really the backbone of how we develop and improve our systems over time. For example, the X7 over there, the dark gray printer on the ground, that's our flagship composite printer. That's been our most popular printer for a long, long time because it delivers the highest precision and strongest composite 3D printed parts in the market today. That printer was built with a high precision laser that does bed calibration. Just helps to calibrate your tool. It's a pretty simple task, and a lot of people can do that manually. We've updated that laser over time and through software to do in-process inspection. So one of the biggest problems with 3D printing today is you print something and you have no idea what you get. You get a part and you have no idea if it's accurate, you have no idea if it's strong, and essentially that laser is now going to tell you how accurate it is and produce a report that you can hand to your customer to say, this is the part that you designed, this is how accurate, it's within the tolerance that you requested, and they can validate that for immediate end use applications versus having to go through a secondary operation of scanning, which adds lead time, adds cost, a new process that you would have to train and educate on in order to get that done. So this is just one example over the years of how we've unlocked these printers to get better over time through improvements that range from print speed increases to new functionality all through the cloud. In short, we kind of steal the Tesla model. The day you buy your car is the worst it's going to be. Over time, that car gets better, gets faster, it has a better user experience, and we do the same thing with our printers. So when we talk about mitigating risk of an investment, when you buy a $100,000 printer and you're looking at the return of your investment, that printer gets better over time, therefore limiting the depreciation. There we go. Limiting the depreciation and the value of that printer less, so that way you can capture more value through more capabilities over time. So when we look at the printer lineup, we kind of have small, medium, large for composite printers. You can see the Mark II, which is this one over here today. We have the X7 that's standing on the ground, and then we have the Metal X in the back. The one in the middle is called the FX20. That's our latest and greatest printer. So capitalizing on what our customers know and love today as an extremely reliable, repeatable, robust platform for printing, and doing it on a bigger, better, faster, larger scale. So capitalizing on what people know and love about Markforged. So this is just a quick video. We can kind of talk about the metal 3D printing process, since it's a little bit different than what we do with plastics.
The maps and levels the bed to ensure the first layer goes down well. Your print is built of two materials stored in this heated chamber above. One of ceramic release material and one of the metal to be printed. This filament material is metal powder safely suspended within a two-part plastic binder. It gets heated and extruded onto the build plate where the part is created layer by layer. The release material gets extruded as an interface between the part and its supports. So once your part comes out of the furnace, it's easy to remove. Unlike other metal 3D printing systems, this process does not require loose metal.
So just one thing to mention here. So with extrusion 3D printing, it's one of the most widely known and accepted modes of 3D printing. So we've simply adopted that with metal 3D printing. So now we focused on continuous fibers and plastics, which I'll talk about shortly. The metal process is basically a print, wash, and sinter process. So it basically simplifies what we know as metal 3D printing today, which is typically done with powders. Powders are dangerous and often very costly and have a very, very high educational curve when it comes to being able to implement metal 3D printing. So our approach with taking our Mark II and our X7, and we've transform that to do metal 3D printing with a couple of different added steps. So essentially, this is what we are going through here today. So we have our printing process, and then we go through a curing process with a chemical, and then a sintering
However, with a
process.
quick changeover, the system is capable of printing in stainless.
Here you are cooperating between the big one and the small one.
No, so the metal printer over there requires two other units. One is a chemical solvent, which is a very harmless chemical that basically debinds the part, and then it goes into a sintering process, a furnace essentially, which cures it as a fully metal component. So where typical systems use lasers or to basically melt the metal, which is obviously very high energy consumption, obviously difficult to maintain and upkeep and expensive to. This is simplifying the process to a simple extrusion system, and then taking your part, moving it to one system, taking it out, moving it to the next. So it takes it a very complicated system and makes it very, very hands-off, and with the same educational curve that you would expect from a simple plastic printer that you can buy for $1,000. So when we talk about the educational curve with students, this is where people would start, and they would simply migrate to, after learning this, to the metal process. So making it very, very scalable across the lowest common denominator, right? When we look at additive manufacturing, you might have somebody who's never touched 3D printing. They could be a machinist of 40 plus years who know how to work with their hands. And then you might have a student that has 5 years of 3D printing experience. We try to accommodate to that entire span of educational curve. The people who are brand new and the people that are highly expert. So when we talk about that, I'll talk about that with software a little bit more, but we're trying to make this scalable. And in order to scale, you need to make it accessible for everybody. And then as I talk about the metal process with powder, Markforged is expanding outside of the extrusion style of printing into powder bed systems for high production. So we're starting to grow our portfolio to make sure that we can accommodate a wide range. So small, high precision printing, large composite printing, metal components, as well as high production metal components with this new company that we recently acquired. So when we talk about materials, so we have our platform that ranges from small, medium to large. We do metal as well. We obviously scale that with different types of materials. So our focus has always been plastics and continuous fiber. So what I mean by that, plastics being, what I like to compare it to is concrete and rebar. When you're building a foundation, you need rebar to reinforce your concrete slab, and that's what provides the strength. We're doing the same exact thing with plastics and continuous fiber. So plastics, we have these material onyx. Onyx is our base industrial plastic that is then reinforced with carbon fiber. That takes a part that is flexible like plastic and makes it as strong as aluminum in many cases. And we're expanding that with more high precision materials like Onyx FR for flame retardants, meaning that it's self-extinguishing. So if you're an aerospace company and you need parts that are going to not catch fire, that material will self-extinguish so that way it's flight ready. This applies for oil rigs in many cases. We work with Equinor in Norway, who actually uses Onyx FR and continuous fiber reinforcement to manufacture spare parts and maintenance on their offshore rigs. So that way, they don't need to fly back over to mainland Norway to have things manufactured. They do it on site on their rig. We have lower cost prototyping materials like PLA for quick prototypes, color prototypes, and then we have our full range of metals. 17.4 stainless steel, various tool steels, Inconel, copper. In many cases, you would say, where's aluminum? Aluminum is obviously a very common material in manufacturing today. It's probably the lowest cost, easiest to cut, and most widely available. Where we feel is that carbon fiber parts are often a direct replacement for aluminum grade materials. With carbon fiber, we're able to reinforce our parts and get a part that's stronger than aluminum in many cases, and that makes it a direct replacement for a lot of applications, since aluminum is probably the most widely used material out there. And this is just demonstrating the value here. So traditional plastics being ABS on that top bar, Onyx, our base plastic, which is a little bit higher strength, a little bit more industrial. Then you have your aluminum 6061, and then you have the ability of continuous fiber reinforcement. And with continuous fiber reinforcement, you control exactly how strong your part is going to be. You can have a little bit of fiber, you can have a lot of fiber. So that really gives you the power to optimize how strong your parts are for cost, lead time, and make it a very much efficient process. And when we talk about why people buy Markforged in general these days, and there's a couple of reasons. One, we have an unmatched surface finish. For an FDM process, or FFF, this extrusion, people commonly say that the quality of the parts is no good. The surface finish doesn't look professional, doesn't look end use, and the reason why people come to Markforged is because our parts look like an end use part. They're competitive with injection molding in many cases. One, they have high chemical resistance and high heat tolerance, so they can be exposed to more rigorous conditions, whether that's oil, cutting fluids, water. We use these in hot and cold temperatures. It's a very, very robust plastic that can be a direct replacement for a lot of different metals. And then it's built tough. I had this example right here where this is a lifting rig. We'll talk a little bit more about that case study later on, but it's certified to lift over 1,000 kilograms. That replaces a steel tool used by Wärtsilä for large ship manufacturing. So when we talk about what materials are important, we like to say that the future is composites. We're obviously a metal 3D printing company as well, but what we often find is we have customers that come to us asking for metal, and we find that composites is a better solution because it's faster, lighter weight components, the costs are more optimized, and it's a generally easier process. For the applications where you do need metal, obviously the Metal X is a great solution there, but we see that the composites is becoming more and more of an adopted standard in manufacturing today. So we've talked a little bit about hardware. Now we can talk about our materials as well, and then now we can talk about software, which is really how we scale and adopt additive manufacturing. So with software, our system is cloud-based. So what that means is you log on to Google Chrome and you access Eiger.io, and you have your printing slicer. So essentially what that slicer is your digital inventory. It's your cloud or your slicer management. It's your folder management system. That's how you prep files, choose your settings, and kick it off to a printer. So that's just the baseline. That's Eiger Core. And we're expanding with further software tiers that allow you to have a more enterprise-level functionality and more performance functionality. So I briefly touched upon Blacksmith earlier with in-part inspection. We can talk about that a little bit later, but that's one of those features that are adding to the software tiering structure that we're adopting, so that way you can have more power from a software perspective. So when we talk about software, this is just, so Eiger is basically our backbone of our printing solution. Again, you access it through just the cloud. You log in and you have your entire print folder or print digital inventory via this solution. So you basically log in and you can have 10 parts, 20 parts, 1,000 parts, basically building a digital inventory and converting where you physically store parts into a digital approach. So I go to a lot of companies these days and we see massive warehouses full of thousands and thousands of parts. And our first objective is to identify which parts are suitable for manufacturing via 3D printing and eliminate that space. Eliminate the need for stocking those parts on the shelf, so that way we can shift to a 3D printing process and be able to print at the point of need. So with software, we're able to scale very easily. So with the part slicer, this is essentially producing or getting your parts ready for the printing process. So again, as I mentioned before, we want to cater to the lowest common denominator. Are you a brand new user and you have no idea how to actually 3D print a part? So we try to make it as simple as possible by limiting the number of click downs as possible. So all you're doing is clicking the type of printer that you want. Do I want to print on the Mark II? Do I want to print on the Metal X? And you're selecting that printer, which material you want to produce, how you want that infill structure to look, where you want continuous fiber, if you want continuous fiber, and then kicking that off to the printer. So we have some very, very simple user experiences that can also be scaled to be more complex, so you get more functionality of the system, more customizability. And then you have your build creation. So this is basically preparing the part for actually printing. So being cloud connected, if I'm standing over here, I can easily kick off a print from my computer and send it to the printer and have that immediately started. So when we're talking about lights out manufacturing, being able to print around the clock, this enables us to be on a plane, have Wi-Fi connection, and realize that I want to kick off a print for Monday morning when I get into the office, and be able to manipulate those settings on your phone and send this to the printer, so that way you're not wasting time getting to the office and actually having to play with the printer yourself. So when we talk about adopting this on a global nature, you can have a manufacturing plant in the UK, for example. You can be designing in the US, and that designer can send print files to that manufacturing facility in the UK to ensure that those people who maybe don't know how to use 3D printing have the parts that they need in an easy way to manufacture. You can't do that with CNC machining. You need to have an operator. You need to know how to program the system. So this one makes it being able to deliver the part to wherever you need it without having to physically deliver something. So when we talk about sustainability, supply chain failures, having to ship parts, this is eliminating a lot of those nodes of failure. And then print management. So knowing how to use your system efficiently is really important. So Eiger captures a lot of data to figure out who's printing, what type of printer they're using, what material they're using, so you can assess and make decisions based on this data. So if you know that you're using a lot of material in November, your procurement can then procure that material in October to pen that production cycle. So this allows you to make informed decisions on how you optimize your schedule and how you manage your print farm. And then when we talk about kind of deploying a scale, because obviously most companies start off with one printer and quickly scale to 10 printers, 20 printers, 100 printers. So we have software that's built for that to be able to scale and create this distributed manufacturing. Eiger Fleet is one of those core products that we're offering that allows you to adopt this on a more enterprise level system. So being able to have on-demand printing, your digital inventory, an organized structure for managing your parts, managing your teams, high security features, so that way you know your data is protected, and real-time improvements, so being able to send improvements via the cloud. So when we look at Eiger Fleet, we have SAML and single sign-on. So if you're, again, I'll use the Saudi Aramco example just because they're a large company, we can allow them to use their domain of aramco.com to be able to invite 1,000 users that will then have access to Eiger to be able to log in and start creating prints, kicking off prints, and adopting the 3D printing process. And this is all obviously on the cloud, so it's very easy to scale by just accessing it. You don't need to download a physical program. We have role-based access, which basically gives control to various groups. If you're a designer and you cannot use the printer, you've never used a 3D printer before, but you know how to design, role-based access basically tiers that access to what you have. Can you design and slice parts in the Eiger, or are you a print technician, and can you kick off prints, maintain the printer, and manage that print queue? So this allows us to create this kind of structure in this government to make sure that people with their expertise are focused on their specific areas, whether it's administrators for IT, print technicians, designers, management. You can structure that however that caters to your organization. And then you have integration with various systems. So APIs is something that's we're discussing very heavily with a lot of large organizations. What this allows us to do, having APIs, allows us to integrate with existing systems. ERP, PLM, MES, so being able to manage the health of your printers, being able to integrate with an ordering system. So if I am Saudi Aramco and I want to produce a part, by creating these ERPs, these programs with your ERP system, you can essentially scan a part and have that immediately kick off to your nearest printer. So you can create programs to mitigate inefficiencies in the workflow. So when you talk about scaling a process globally, you'll be able to create these programs that take out a lot of those steps from getting a design to an actual printed part. And then analytics. Building an ROI is obviously important for people to keep reinvesting in technology. So with the custom analytics, you're actually able to plug in existing numbers of parts. So for example, if a tool costs $100 to manufacture today, and to 3D print it, you know that metric is about $10. You can track that metric over time, so every time you're printing it, it's compounding that information. And after 2 years, 3 years, 5 years of printing, it'll give you a metric that says you've saved tens of thousands of dollars on this part. It's time to reinvest, buy another printer, add capacity to your fleet. So this really allows you to create that custom data so you can make investment decisions based on what you've printed over several years. And then the highest form of security for printing. We obviously want to protect your data. So with Markforged, we're the first ISO 27001 cloud certified program, so for 3D printing. So that means we're constantly doing penetration testing, making sure that your software is safe and your data is going to be safe to be able to use on the cloud versus a on-premise solution. And then I talked about Blacksmith a little bit before with the X7. So Blacksmith is a really interesting tool. It's basically autopilot for digital manufacturing that connects part design, production, and inspection with powerful artificial intelligence. So basically what Blacksmith is doing is scanning your part layer by layer, creating cloud point data, and then putting that back into the software. So after your part is done printing, it tells you exactly how accurate that part is to within a single micron. It'll basically give you a color readout that says this area is not so accurate, this area is extremely accurate. And with the AI functionality, it'll continue to improve that printing process over time. So if it evaluates that a part was inaccurate, it'll evaluate that to its nominal CAD and make assessments to improve that part over time. So this is a really, really powerful tool that's going to kind of close the loop between what we print and what we validate and deploy in the field. So when we look at traditional processes today, there are a couple different ways to do quality control on parts. There's visual checks, caliper checks, separate inspection processes, and now there's in-process. So these create a lot of inefficiencies and inconsistencies between process. If you're doing visual checks, one operator can have a different visual check than another one. If you're doing caliper checks, this is obviously manual and cumbersome and riddled with inaccuracies based on the manual aspect of it. Then you have expensive separate in-process inspection tools. This could be a $70,000 inspection arm that needs an operator that's trained and knows how to use it, and that also probably comes with software costs year over year. So what we're trying to do is build that process into one single system, so that way when you print your part, you know exactly what you get immediately, and you don't have to go through a 3-week lead time of having that scanned before it can be deployed in the field. So a couple of the features of Blacksmith are customized quality reports. So when you print your part, you can get a printout of your report that says this is how accurate it is. You can evaluate critical features, and you get precise data visualization. So we obviously learn by what we see. So having that color readout is really, really important to be able to quickly make decisions based on that color readout to say this part is inaccurate or this part is accurate. And the future of that is looking at expanding to more simulation. So we've talked about printing parts and knowing exactly what you get from the printer. Now we want to look at the before that, where you can do your prototyping. So in order to validate that a part is going to work in the field, you need to test it, you need to change settings, change design, and validate that it's going to be strong enough to withstand that application. So our recent acquisition was Teton Simulation, and we're integrating their software that's going to do predictive simulation of your parts. So when you're introducing a composite part that's reinforced with carbon fiber, it's going to tell you, does this part pass your loading conditions? Is it going to work in the field? And if it doesn't, it's going to give you optimization to tell you, add fiber here, change the material, change the infill density, change the design. So that's going to really solve a lot of the problems that people have with the iterative cycle of prototyping. So I've talked a lot about kind of our technology. Now we can actually look to where people are using it in the field. So Siemens Gas and Power is one of our largest customers today. For example, they have about 7 of those printers, the X7, in Sweden at their branch in Finspång. And the big problem that they have is being able to do maintenance on their turbines. Often they need to do that in the field, or if maintenance is critical, they need to actually bring that turbine offline and do that at their facilities. So what they were looking to do was to develop maintenance tools that were able to do profiling of their turbines in the field. So being able to basically profile the turbines that were damaged and get the correct profile back so that way they can get back operating. So this is a turbine chasing saw that we're looking at here. Originally this was just meant to be a prototype. They did it with Onyx with continuous fiber. And what they realized was the material was high strength enough where they were actually able to adopt this as an end-use part. So Siemens operators and technicians are actually using this part in the field to maintain their turbines, which is saving costs, saving lead time, and getting their systems back up and running quicker versus having to bring them offline to do that maintenance. We work very closely with Shawcor, and this is just a simple example of being able to replace aluminum. Continuous fiber with or carbon fiber reinforced parts was a direct competitor with aluminum in many cases. So on their manufacturing floor, they were able to identify various aluminum parts that they would have to outsource to third parties. That would take long lead times and obviously high costs, and bring that in-house, bring control of that process. So they were able to basically identify 53 unique 3D printed parts, replace them with carbon fiber, and that basically saved them 27,000 Canadian dollars over this time. So that immediately has the return on the investment of buying a Mark Forge Mark II by just looking at these 53 parts. So when you scale that in a large organization that might have 100 parts, 1,000 parts, 10,000 parts, you can see the value increases dramatically and exponentially over time. Vestas is one of our most recent customers. So we're looking at, obviously, being in Kuwait here, oil and gas is probably one of the largest industries that we know and see today. So we're looking at kind of gas and power. We have Canadian oil field manufacturers, and then now we have also on the other end of the spectrum with alternative energy with wind power. So when we look at kind of competitors in this field, Vestas is adopting manufacturing for a couple of reasons. The main reason is they had a program to implement additive manufacturing. They said they wanted to adopt it, and they were going to find the best solution to bring that to their company. The reason why they found Markforged was because we're known for reliability and repeatability of our systems. So they wanted to eliminate the inconsistencies that they were seeing with their hundreds of suppliers that they have globally. So if they're in a branch in the UK where they might have 10, 20, 30 suppliers that are all manufacturing specific parts, each of those suppliers manufacture parts in different ways. And when they get those parts, they need to inspect those parts to make sure that they are up to the quality that they requested. So this is where Blacksmith really came in for Vestas. For them, they were able to print that part with the Blacksmith report, validate that they got the exact part that they needed, and then they could immediately deploy that in the field without having to go through a 2 to 3 week lead time of inspecting that part with a third-party inspection process. And where Vestas is kind of scaling today, so they started off with a couple printers. Now they have about 22 printers globally. They've made an investment of well into the millions of dollars with Markforged technology. And the future scope of that is on the magnitude of 60 to 80 to hundreds of printers scaled globally in various locations. Today they have them in the US, in the UK, in Denmark, in India, various locations. They have multiple printers at each of those locations. And this is just with composites. The next kind of iteration of this is looking at metal 3D printing to actually produce lightning tips that go on the end of their turbines to protect their products. So when we talk about creating this additive manufacturing print farm that is connected via this network, we're really democratizing manufacturing. And essentially what that means is giving the power to the end users. You give the power to them and they're able to create efficient processes without having to rely on third parties and be dependent on a conventional supply chain. They're able to take control of that and really democratize how they manufacture parts today. So a couple of other examples. Tooling and fixturing is kind of our bread and butter. So when we talk about replacing aluminum, carbon fiber is a direct replacement in many cases there. So when we're trying to identify applications that are right for 3D printing, especially the Markforged platform, it's easy to look at conventional materials out there, steel, aluminum, and make direct replacements with a continuous fiber process. In this case, this company, Lean Machine, they manufacture these vice grips, or they typically buy them from a third party. They can't do much customization. They just have to deal with what the supplier gives them and be able to use them to their best ability. With this process, they were able to be extremely limited with the parts that they manufacture. So within their CNC machines, this big chunky vice grip was basically too big to be able to manufacture the part that their customer requested. So what they did was they took this design and reverse engineered it to be a composite process that was comparable in strength, so it was able to meet the demand for actually making that part and dealing with the rigors of a CNC environment, and also be lower profile. So the tool is lighter, it's less material, so that way they can actually machine this part in whole. So essentially the problem was the part was too big with the vice grip to be able to machine. So they had to reduce the profile of the vice grip, that way they can machine the specific geometry that they were looking to get out of this part. So this part typically takes about 3 weeks to manufacture, costs about $6,000, and when they reverse engineered it to do it at composites, and this is a multi-part assembly, it took about 1 week and $1,500 to manufacture. So that's a 66% reduction in time, and that's a 75% reduction in cost.
Same quality?
Same quality, same quality.
100%?
For the most part, yeah. Obviously, with continuous fiber, you have the ability to control that. It's not going to replace all the mechanical properties of a metal part. For example, wear and tear. Plastic wears differently than a metal component. But when we talk about strength, in many cases, it's a direct replacement.
Over the lifetime?
Over the lifetime, yeah. So for the lifetime, it depends. Metal is definitely going to have a higher lifespan compared to plastics because they wear much easily. So that's where we talk about hybrid components. So I can actually skip ahead real quick while we're on the topic. So hybrid components is definitely one of the aspects that makes our solution extremely competitive. One, because you can manufacture lighter weight components with carbon fiber, and where you need metal, you can make small metal components that help increase the lifespan. So for this part, this is basically a fixture or an end effector for transferring an axle during a casting and machining process. So they cast the axle, and then it needs to go through a machining, and it needs to transfer this very, very heavy car axle. This part is traditionally manufactured out of metal, but they wanted to obviously reduce weight, reduce cost, be a little bit more responsive. Composites wore out too quickly here because they were dealing with a metal component that was smashing into the part. So it was high strength enough, but the surface wore through to the point where those parts need to be replaced more frequently. So in this case, rather than machining the entire part out of material or out of metal, or printing the entire part out of metal, all we needed to do was redesign it to have a composite base, which makes the tool a lot lighter. And then when the metal wear pads, which are printed on the Metal X, wear out, all you need to do is replace those small little parts that are about this big. So printing this out of metal would be much, much more expensive. But the composites create a much more economic approach to doing this, and now you have a multi-part assembly where you're stocking small parts versus very large parts, so reducing that inventory cost. So there are going to be parts or examples where metal is definitely required. Composites is not the solution for all things, so you have this really competitive edge by being able to design and prototype in composites in some case, and then all you're doing in the software when you want to go to your final part is clicking a drop down and saying print in metal, and now it shifts that design over to metal, and you go and print that part out. So that's where the software aspect makes us very competitive for being able to cover the entire spectrum of parts. Plastics for prototyping, and maybe some non-loading conditions, continuous fiber for high strength, and then metal for wear and tear applications. Maybe you have pressure vessels that need to be fluid tight, or they need to have extremely high heat resistance where plastic would typically melt. So a great example of kind of non-load bearing applications for plastic is with this company, Cabin Management Solutions. So all the parts that you see in gold on this bottom picture here are gold-plated onyx. So those are plastic parts that are actually going onto a plane, manufactured for end use, not for prototyping. Being the material is a chopped carbon fiber material, so it has nylon with chopped carbon fiber, it actually holds somewhat of an electrical charge, so it's able to be plated with various types of metals like nickel, gold plating, we've done silver plating, and that really produces a unique end-use component. And the reason why this material was able to go in the plane was because it's V0 certified, which means it's self-extinguishing. So in order to go on this plane and be an end-use part, you need to be certified for aerospace. And the only way to do that was to have a material that was self-extinguishing and that could meet this criteria of also having high surface finish that can also be plated with gold. So that was really the benefit for this customer in this instance. Legacy components, we see this a lot when me and Abdullah talk to customers, especially in the oil industry, is we have a lot of parts that are wearing out. We have no idea how to manufacture them because we don't have CAD files. So legacy parts that are basically going extinct because there was somebody that manufactured them 40 years previously. They're no longer working, and now they need to figure out how to reverse engineer that part and manufacture it. The problem today is that there's not a lot of people, or there's a diminishing group of people that know how to cast components, or that know how to do machining, or know how to process and do conventional modes of manufacturing. So we're moving more and more to a workforce that is digital, working in CAD, and focused with 3D printing. So when we talk about the demand or the value of 3D printing, is you're converting to a CAD design versus a manufacturing process. So in this case, this legacy component had to be, they basically had one left. They couldn't source this part anywhere in the world, and it was a carburetor for an old 1960s car. They had one part. They basically scanned it, redesigned the part, and they needed to be able to manufacture that in some way. They got quotes for casting, they got quotes for machining, and it would be economically inviable for them to do that for this project. They would have gone bankrupt just trying to make this one part for this specific contract that they had. So what they did was prototype this in plastic, validate that the design was exactly what they needed. They test fit it. So they actually implemented it in the car and ran it for a second. So this actually worked as a composite part as a supplement to this carburetor that's typically made out of steel. They then took this, changed their drop downs to metal, printed it in metal because the printing process is virtually exactly the same for going from plastics to metal. And then they were able to implement this as an end-use part that's functioning in this car today. So you can apply that in a lot of different areas. But the key aspect here is that this is a part that nobody manufactures. It was impossible to source. The only way to do it was to either go through options that would make your business go broke, or to 3D print it in a way that reduced the cost to hundreds of dollars versus thousands and thousands and thousands of dollars to manufacture. So we just talked about Dana a little bit in terms of this specific part. So just to back up and talk about what Dana is doing, Dana is one of the largest manufacturers of car axles and transmissions in the world. So they're a large industrial company. And what they were really trying to do was bring that age of old-time manufacturing into a new age. So this wasn't necessarily a manufacturing problem. It was an HR problem. It was a people problem. Because they have 65-year-old engineers that have been doing traditional manufacturing for years and years and years that they wanted to convert into additive manufacturing. So the reason why Dana chose Markforged in this solution was, yes, we're easy to use. The system's very reliable. You can beat them up and they're going to work and they're going to produce parts for you. But there was really no companies out there that had a great educational tool. So with Markforged, we have Markforged University, which is basically a self-service online tool that allows you to learn design for additive manufacturing. It learns how to operate your system, how to get the most value out of possible. So this was predominantly an HR issue with how do we find the right people and how do we train them effectively to use the system. Because all in all, you can buy $1 million machine for 3D printing, and if you don't know how to use it, if you're not trained properly, and you don't know how to identify the right applications, it's going to fail. You're going to have a big, expensive metal box that's sitting in the corner collecting dust. You need to find value for your printers, and the way you do that is by educating early in the process so you have early success that you can compound on. You drive value through success, not through failures. When you have failures early on, people get deterred from using the technology, and they tend to do what they know. So in this case, that's where Dana found their value, and there again another instance where they bought 2 or 3 printers in the U.S., and they've now scaled that to a print farm of 40 printers globally, making a $3 to $4 million investment in 3D printers.
Any of them in the Middle East?
I don't believe Dana has any branches in the Middle East at the moment. We talked about Wärtsilä. Briefly, this was the lifting tool that's certified for over 1,000 kilograms of lifting capacity. There's a couple different aspects that make this a really, really interesting case study. One, it's the first CE certified tool in the industry for composite 3D printing. So when we talk about 3D printing, it's really difficult to get this validated for actual in the field use. If you're an industry that needs to certify parts, this is a big hurdle for 3D printing today. So this is a huge step in the direction of we've printed a part, we've validated and we tested it, and we've approved it for actual using it in critical situations. And this situation was they needed to lift a piston that's going into a large diesel engine that weighs about 240 kilograms. So this is a critical, expensive part that they need to ensure does not drop and break, and that's extremely heavy, and they need to basically assemble this. One of the biggest problems here was safety and health requirements for this part. This big yellow tool that we see here, that is a massive steel part that takes weeks and weeks and weeks to machine. It's extremely expensive, and it also weighs a lot of, it's extremely heavy. So the problem with this is that they had 2 operators that required to set up this tool. So they needed 2 people to do this setup instead of having one person do it and the other guy focus on more critical operations. By printing it, they were able to reduce the weight of the tool, so now only one person needs to set up. It's needed to have a factor of safety of 4, so that means it needed to lift 4 times the amount of the actual weight of the tool, or the piston, which was about 960 kilograms roughly. And they wanted to understand when that tool was going to fail as well. So with the 3D printing process, when we talk about smart tools, you can actually stop prints, embed sensors, embed magnets, NFC chips, hardware components to make them better, more efficient tools. So in this case, they actually embedded a stress sensor into the part. So they printed it, put in the sensor, and then printed over it so it was permanently embedded in that component. So now they have a digital readout of when that part is going to fail based on that stress sensor. So when they need to reprint the part, based on when that's getting to its final loading capacity, they can easily start a print and have that ready to go before there's a failure that's going to occur. So it's mitigating risk of a failure and a potential incident based on creating this smart part that's assembled together via this 3D printing process. So this is a great example of a very complex tool, very strict requirements, need to be certified. But in many cases, this isn't what people are doing as well. Some things can be extremely straightforward and very, very simple. These are the non-sexy parts. So when we look at 3D printing, a lot of people like to create very complex geometries, organic structures, things that look very pretty and bright colored and fun. But in many cases, what the average manufacturer is doing is making very, very simple tools that accomplish a very, very simple job. And these are often the tools that drive the most value for customers. So in this case, MF Precision is basically making soft jaws. And all that's doing is clamping a part together that can be then machined in a process. The other one, the first one on the top, is an inspection process. So it's just another fixture that's sitting idle on a table where it has a probe that's measuring how accurate that part that they just machined in. Typically what they would have to do is they'd have to machine these out of aluminum, and that means that they're taking their CNC machines to make tools to make their actual end-use part. When you're making tools, you're not making money. You need to make money through your revenue-generating parts. So your 3D printer is your operator, your one-time cost operator. You pay $20,000 US for a printer that produces your tools while you make critical parts on your $300,000 CNC machine. That's where you make your money, and this one is focusing on making small parts that you would typically don't want to spend your time on. And this drove a lot of value for this team. 19x faster lead time and 2.5 the times the cost savings per these parts. And this is, before I finish up on the applications, this is a great example of an extremely complex metal component used in an area that is extremely stringent. So this is a cutter body. When you're machining parts, you obviously need cutting tools. So this goes into a CNC machine that's then cutting your material. And there's a lot of things that play into how you cut parts and how you actually get your final component. There's speed rates, how fast are you spinning this tool. There's cooling, you need to be able to cool it quick enough. And those all play into how quickly you can manufacture components and how much you can optimize for this process. So for this one, they basically had a company come to them. It was Volkswagen that basically said, we need this cutting tool. Our supplier can't get it to us at the moment. We need something ASAP. In order to go through this process of validating and creating this tool, it would be weeks and weeks and weeks of prototyping, iterating, and testing on processes that would be traditionally machined. In this case, they basically took their 3D printer, they printed it on the Metal X, they added a few carbide tips on it that would actually cut the metal. They added some helical cooling channels that made the part cooler, so that way you could spin faster, and it was also a fraction of the weight. So when you compare this to its machined counterpart with traditional manufacturing methods, it was cheaper, they could make it faster, it could spin faster and cut material faster than the traditional way of making it. So this design can only be manufactured with 3D printing because you have these internal channels that are spiraling through that part that allow it to be cooled. You cannot physically manufacture that type of geometry without segmenting this part into multiple different components or compromising that geometry with a more simple approach, maybe drilling one hole straight through, which would be less performance. So I know I've been talking about for about 45 minutes or so we'll get to basically questions, but just to recap things in terms of business value. When looking at additive manufacturing, we want to identify business opportunities. So this is that same slide that I showed earlier. Digitalization, products, and responsiveness. These are the things that we commonly hear. We want to be able to respond to suppliers faster. We want to build a supply chain that's resilient and that you can rely on. We want to have products that are competitive with their traditional counterpart, but also more cost effective, have faster lead times. And we want to be able to convert that to a digital inventory. We no longer want to store thousands of parts in a warehouse that sit there for years and years and years waiting to be used. We want to be able to print when we need a part rather than having to store it. So when we look at business value, we obviously talk a lot about tooling costs, and we talk a lot about lead time. But there are a lot of other value that can be captured through additive manufacturing. That could be ergonomics and lightweighting, getting a better part that feels better in an operator's hand that allows them to accomplish their job better. reduced injury rate, whether it be lightweighting that tool to make it a simpler operation where you're not putting your critical technicians at risk. Attracting the brightest stars. When I was in college, we had 3D printers, and I wanted to work for a 3D printing company because I thought it was the coolest technology out there. So as a mechanical engineering, I was attracted to companies that had this type of technology, and I found myself actually working for a 3D printing company. So this is really important when most of the skills that are being taught in schools are CAD design, and 3D printing. In order to attract those best and brightest stars, you need to have that technology in-house. So when we talk about implementing 3D printing, there's obviously a lot of steps that go into play. You need to build a strategy in order to adopt it. Because as I mentioned before, if you don't educate, if you don't build a process to actually implement this in a workflow, it's often going to fail. So we need to, one, discover and qualify business problems. We need to identify the value at stake. Are we leaving revenue on the table because we have to turn people away because we can't manufacture that specific part? Do we have a team that's going to focus on this, that's going to be the internal champions and drive this forward to actually building it into a process? Do we have a validated technical assessment? Have you made sure that the parts actually work for the applications that they're intended to be used? And do you have a plan to execute? So pretty much at this point, this is where you would adopt additive manufacturing. This is where you would buy a system and put this in your machine shop. In order to execute that efficiently, you need to be installed and you need to be trained. You need to have education available, and you need to be able to realize that value. So these are the things that you need to consider when looking at investing in 3D printing. And then there's 3 other aspects. There's people, there's process, and there's technology. If you don't have the right people on the project focused on driving additive, it's often going to fail. You need to be passionate about it, and you also need to be educated and have people that are going to be internalizing this investment over time. You need to build a process. So, finding the right materials is good, finding the right printer is good, but if you don't have a process for implementing it in a strategy that's scalable, it's often going to fail. So making sure that you have a process for storing your files, being able to collaborate internally, having advanced analytics to be able to build automated ROIs. And then obviously you need to have the right technology. You need to have the right printers that are built tough. You have to have the right materials that are going to be operate in the actual end use environment. And you need to have the backbone of software that's going to be, protect your data and make it scalable and adoptable for the entire organization, not just a select few. And finding the right application is definitely probably the trickiest part about 3D printing. There's a sweet spot. And what we see with the yellow points on here is kind of where Markforged is most focused on. Tooling and fixturing are often very, very low risk parts, but high reward. When you focus too much on high risk parts, high reward parts, it becomes a much, much more challenging approach. So in order to adopt and scale additive manufacturing effectively, you need to find the right applications that are simple enough to be able to learn, create success early on, and then scale that. To go bigger, try different materials, try more critical applications, and as you build that proficiency, you can then move to for example, a powder bed system with our digital metal solution that allows you to scale production volumes in the thousands and thousands of parts for metal 3D printing. And education is obviously extremely important. We want to maximize the impact early on, accelerate adoption, and build on existing experience. So Markforged University is a great tool where people at self-service, it's about 15 to 20 hours of training online that allows you to access various critical skills in the additive journey early on so that we can have skills that can be adopted and scaled. So, transforming your business, what does additive manufacturing do? It secures a competitive edge, increases profits and revenue, and creates more productive and efficient manufacturing processes. And this is where a lot of our companies see the value. If we build an ROI, this is just a great example of how traditional manufacturing can compare to an additive strategy when you look at lead time, part cost savings, ROI over time, and the market opportunity of how much value you can capture. And it's important to have an investment strategy as well. Creating pilot systems where you have an introductory phase that allows you to play around with the technology, have easy, low-risk applications that can then be expanded to more critical applications with more complicated technology, whether that's starting with plastics, moving to continuous fiber, and then going up to metal, and then maybe looking at production. And then obviously you want to be able to know what you're getting out of your system. So tracking success rates, how many parts are you printing? How many printers do you have under your organization? How many users are currently operating your system? So being able to leverage the data that you have today to scale it, bring more printers in-house, and get the most out of your system to make them as efficient as possible, so that way you're manufacturing around the clock. And always build a plan. Building a plan over time is important, and sticking to those various steps is how people are successful with implementing additive manufacturing. So this is pretty much the end of the presentation. So I guess we can leave it to questions at this point.
You have a mic. يا جماعة اللي عنده سؤال يتفضل يسأل. عربي إنجليزي ماكو مشكلة. Okay, so anybody has a question, you can ask.
Thank you, Kyle, for the interesting presentations. We have met earlier, maybe through the MS team. This is Lamia Al-Kendari, team leader, research and technology in KMPC. The way that you presented the technology, it looks like the spare part will be ready immediately after it gets out of the printer. So is there any requirement for any heat treatments to reach to the required specifications, or this is something that you can control while you are, running the printer environment?
Yeah, that's okay. Yeah, so that's a really great question, and it's a challenging one to answer. So with every process, there's obviously a learning curve and different requirements. Obviously, when you look at a casted component compared to a machined component, the mechanical properties are very different, and you need to obviously look at what the end result is going to be, right? So what we always talk about is, in the industry, is we're not in the business of replicating. We're reinventing, we're re-engineering a part for the process. So when we take a part and we see that today it's manufactured via CNC machining, it's a specific material, it goes through a specific heat treating process, and it needs to be, and has a specific strength of this. I think what we need to keep in mind is that it's about the end result, not necessarily the process of steps getting to that end result. So in many cases, if something is manufactured out of 17.4 stainless steel today, that doesn't necessarily mean that we can't accomplish the same job with a different material that has different mechanical properties, right? So obviously looking at the process of implementing 3D printing at the result of the part. Doesn't necessarily matter about the tool that's actually getting into, but at the actual end of the part. So when it comes to certifying for a process, whether you need to heat treat, for the it'll depend. That's the unfortunate answer, is that it obviously depends on the application. In some cases, you need to do higher heat treating on the materials to get higher hardness. For example, on the D2 tool steel, we actually have a sintering profile that does a quicker cooling, so that way you get higher hardness out of the sintering of it. And in some cases, you need to take that part and put it in a heat treat oven in order to do some processing on that part. So our data sheets actually explain a couple of different situations where you can accomplish various hardnesses and higher mechanical strengths based on those profiles, or by additional ASTM standards for heat treating. So yeah, it's a difficult question to answer, because it's obviously going to depend heavily on the application. But it's obviously, you can look at that from a couple of different aspects. So making sure that if you're looking at 17.4 stainless steel, because that's how you make it today, looking at options for using other alternative materials that might accomplish the same job, but just in a different form. Hope that kind of answers the question. But
Any other question?
Thank you very much, Kyle. Actually, my question is a little bit different than the other questions, not related to products. My name is Mohammed Farjab. I'm from Computer Engineering Department at Kuwait University. My question is, actually, I'm interested in the Mark Ford University.
okay.
What kind of programs can you give us a little bit more details about?
Sure.
From the education.
Yeah, and I really do like that question, because we often talk a little bit too much about products as an additive manufacturing company. We get very focused on what it does, how fast it is, and I like to separate from that, because the additive journey is much more than printers, right? So education is obviously extremely important. Today, what we have is Markforged University Online. So that's basically licenses of an educational platform that goes through a series of modules that start from basic and get more complex as you go through them. Those are ones that you can scale very, very easily by just buying licenses for basic students to be able to educate them, or operators, or whoever it might be. Unfortunately, with COVID, what happened was this was typically an in-person process. We actually had a team that would come out to various locations. If you bought a Markforged University basically educational package, we would actually come out and run a system with alongside of our partners, like Rapid Manufacturing Technology, and do this training at your site, whether that was with a group, maybe that's a group of 20 people, maybe it's a group of 2, and you basically get that training over a couple of days. What we also had was training the trainer, and this is basically taking experts from Markforged, training somebody at your facility, whether that's a professor or whether that's a machinist, whoever it might be, and actually training them to give this training for future groups. So really giving you the power of the tool of that training to be able to educate a much, much wider base of students or operators. So yeah, that's pretty much my question. Does that answer the question? Or are you looking for some more clarity?
Yeah, it's actually I wanted to know if there is maybe an educational setup that you have in place that goes with this university program. The reason why I'm asking this question is that if we are interested in introducing such a technology to our students, I do understand that you have this train the trainer, maybe this is something we go for, but
sure.
I mean, at the end of the day, a majority of the product that I've seen, at least the one that you explained, it seems like it's more of a production kind of machinery, and I'm sure you're very familiar with the need for people to understand the technology, and you need to introduce it in the proper venue where we build expertise within the region and introduce the technology there. So I guess maybe you do have some kind of an educational platform or suggestions for such educational program. A particular printer that needs to be there, the kind of investment that needs to be there, and what goes on with the university program.
Right. And so when we're talking about products specifically, you had mentioned kind of production industrial grade, because that's obviously what I talked about a lot in our presentation. What I didn't really talk about too much is the ease of use of this system. When it comes to the physical printer, when we look at success rates of the printer, they're upwards of 95% and above. Compared to traditional traditional 3D printing, those success rates can vary from 20% to 80%, 90%. And that's all based on what material am I printing, what's the platform, how hot are the nozzles, how fast am I extruding, what material am I using. So the benefit of having this full solution with printer that's manufactured by one company with material that's designed specifically for that printer eliminates a lot of the inconsistencies or the need to tinker and to mess around with the printer to get something to print right. So when we actually talk about this system, it's actually ideal for educational institutions. So the Mark II, for example, is an extremely robust printer where you can have brand new users that beat it up. They use it improperly, they break it, and it often, in many cases, continues to work under those conditions because it's built extremely rigid. So when we look at our competitors in the field, for example, Ultimaker. Ultimaker is a great company. They do what they do very, very well. They have a lot of open-sourced platform, lots of materials, lots of settings. The problem with that is you often have lots of failures. And again, as I mentioned, failure is good. We learn from our mistakes, and it's probably a great tool to learn 3D printing. But when we're trying to learn how to make parts, how to design, how to create a mechanical assembly, it's important to have high success rates early on to continue to want to use in that system. Otherwise, if we have something that's continually failing, maybe the parts aren't strong enough, we often see that it's not viable for future growth. And that's what we're trying to build with an educational program, right? We're trying to adopt and build skills for future utilization. So in many cases, the Markforged platform, whether it's a Mark II or an X7 or a Metal X, we have educational institutions that have a similar setup to RMT, where they have 3 Metal X's, a wash station, and a sintering furnace, as well as industrial composite printers, all under the same roof. and it's strictly for one, educating how to use 3D printing, but really trying to get people to make parts. Because the future of that generation that's utilizing that systems, they're often going to see it in the field. So a lot of our customers, I mean, if you go back to one of my first slides, we have 15,000 clients, or 15,000 printers scaled globally. There's a great chance that the next engineering company a student will go to may have a Markforged printer. So when they're looking at developing a CV and they say they've been exposed to Markforged technology early on in the process, and they want to be able to run a print farm at a Siemens, at a Saudi Aramco, at a Vestas, that is valuable skills that they've already learned and mastered in their school and educational systems prior to actually going to the workforce. Does that make sense? Yeah.
I think that's it for the questions. So thank you very much, Mr. Kyle Mason, for the great presentation. And if somebody interested in the presentation that you just finished, is there like, you post that presentation somewhere, or?
Yeah, I can provide my contact information, and I can send you the presentation, or I can send it to Abdullah and he can share it. But this is all information that you guys can have readily.
If anybody interested, you can, get the presentation. Thank you, Kyle.
Yeah, thank you everyone for your time.
Now we have a memorial played by the founder, engineer Abdullah Safar, will honor Kyle Mason. تكريم من المهندس المؤسس عبد الله الصفار للسيد كايل ميسن على حضوره